So let's jump into it. So last time we noted on a TS diagram that it's good for performance to bring in heat into the cycle at high temperatures. Bring in all of your Q in high temperatures and reject all of your Q at low temperatures. So if you push that, if you keep that concept, then you see how to try to improve the performance of the Rankine cycle. So on a temperature entropy diagram with the dome at high pressure line and low pressure line, instead of taking saturated liquid and passing it through the turbine, go ahead and superheat it, because as you superheat it, that amount of heat is coming in at relatively high temperatures. That's going to be good for performance, superheating. When you do that also, it's good for performance in the sense that you get higher quality on the exit. Now, it doesn't really do well if you have superheated vapor still on the exit, because you're going to put that into a condenser, and this heat is being rejected at a little higher temperature than it needs to be. So, but we'll talk about that in a minute. But the idea is to put in heat as high temperature as possible. You can achieve that by superheating. Also, we're going to talk about later is when you put it through the pump, there's a lot of heating that goes on to bring the liquid up to the boiling point at that pressure. And this heat right here is into the system. It's coming in at a relatively low temperature, and you would like to look for a strategy for fixing that. So the two strategies we'll talk about today are superheat. So you're going to superheat the steam, not just have saturated vapor going into the turbine, but it'll be superheated. And then what they call regeneration. And that is using some lower value steam to mix with the feed water before it goes into the steam generator to try to bring up that temperature of the feed water from here up to there without using the heat source from maybe your coal or natural gas or nuclear power plant. So let's talk about first superheating, and then also I should back up. I should also say one of the strategies if you want to bring in a lot of heat is not only to superheat it tremendously. Often there's a metallurgical consideration or maximum, it's a limit, temperature limit. So what you'll do is you'll superheat it to the maximum that you can, and then you'll expand it to an intermediate pressure. So you'll have another pressure line like this. You'll expand it down and then reheat it and then expand it. So you're bringing in more heat at a relatively high temperature by reheating. Reheat. So superheat, reheat, and regeneration are three strategies to improve the thermal performance. So let's talk about the Rankine cycle with superheat and reheat. We'll sketch out how that's accomplished. Here is a steam generator. Steam comes out. This time when it comes out, it's superheated instead of just saturated vapor. It'll go into a turbine, but we're going to have two turbine stages. So we'll have like two turbines, the high pressure turbine, the low pressure turbine. They'll go into the first turbine stage and come out of that turbine and go back to the steam generator for some additional heating before it goes into the second turbine stage, which is a low pressure turbine, because the pressure is dropped. And then after the second turbine, you go to the condenser, and from the condenser go to the pump, and then from the pump back into the steam generator, like that. So the steam generator adds heat on the first pass, QSG. It's like your standard pass, but then it also has some heat added in the reheat, RH for reheat. So there's two heat sources into the working fluid, or two locations where heat is added. We have states. Let's go ahead and label state 1. That's traditional. State 1 is the inlet to the first turbine. State 2, after the first turbine and before you reheat. State 3 is after you reheat. Oops, I already have state 3 there. Then state 4, then state 5, and then state 6. And as you approach a problem like this, you want to make a table and organize your properties, because to analyze the system of the performance of the system, you'll see that everything can be related into terms of enthalpies, at least for this problem. So maybe the Q in the steam generator, if I just look at that, it's going to be an energy balance around that fluid stream right there. It'll be H1 minus H6. And then the work out of the first turbine, something like I'm trying to calculate this W out of the first turbine, and then we'll calculate the work out of the second turbine, and then the work into the pump. That work out of the first turbine stages in terms of changes in enthalpy is H1 minus H2. So you do an energy balance, control volume analysis. You assume the turbines are adiabatic, which is our standard assumption. You get H1 minus H2. And then Q reheat, that's going to be H3 minus H2. And then work second turbine will be H3 minus H4, and Q out of the condenser, I should draw that right here. Q out of the condenser, the direction is out so that we have a positive entity following the notation of the textbook. It's H4 minus H3, and then the work of the pump is going to be H6 minus H5. And just a little aside, when we calculate the work of the pump, we often just do the specific volume at 5 coming in. It's saturated liquid. You want saturated liquid coming out of the condenser. And you multiply it by P6 minus P5, assuming it's reversible. So that would be our minimum work for the pump. All right. Once we calculate all the Q's, W's, then we can do work net out. The work net out of the system would be what the first turbine stage produces, the second turbine stage produces, minus what the pump consumes. Likewise, Q net in is going to be the Q from the steam generator first pass, Q on the reheat in the steam generator, minus Q dumped out of the condenser. And I recommend that you always check that these are equal, because if they're not, look for an error. Energy is conserved for the whole system. So W net out must equal Q net in. Then after a lot of work, we finally get to properties that characterize the overall performance of the system. The thermal efficiency, that's going to be the work net out divided by only the heat in. I know that Q net is the net heat in, which is you subtract off QC, but just the amount in is in the steam generator plus the reheat. See that for the thermal efficiency? And then the back work ratio is the work of the pump divided by the work out of the turbine 1 plus work turbine 2. So these are, especially the last two, are the bottom line. How is the system performing? Yes, sir?
Well, the Q for the condenser, not Q5 minus Q4?
Every time I do it, this is the way I do it. I try to help you. And this goes for the steam generator and all the turbines. Think of enthalpy as energy content. And the higher the enthalpy, the higher the energy content. So if I take a look, I'll say, let's say H1 versus H2. Which one is larger, H1 or H2? This is the way my mind works. I do this all the time. I'll say H1 is larger, and then some of that H is converted into work of the turbine out. So that'll help me write WT1 is H1 minus H2. So let's come down to the condenser. You're going to reject some heat out of it. Which H is going to be greater, H4 or H5?
We'll be on H3.
This is 4, and this is 5 for the condenser.
But in the equation that you have written across, the QC is equal to H4 minus H3.
Then that's wrong. Yeah, thank you for correcting that. So it's H4 minus H5.
Also, the work of the pump,
Yes?
should it be 5 minus 6?
Okay. Which H is larger? Is 6 larger than 5?
So you're putting into it, right?
You're putting into it. So is 6 larger? It's larger than 5. So 6 is larger than 5, and we want a positive work of the pump that's required to make the pump work, right? That's a work into the pump. So WP is H6 minus H5 is a positive quantity. Make sense? Okay. Thank you for any other. Do I have any other typos or miswrites up here? Okay. So the strategy is make that table, and in that table I recommend that you put the state 1, 2, 3, 4, 5, 6, and then put the pressure maybe in consistent units like kilopascal, temperature in degrees C, some quality or description, some enthalpy, some entropy. And then start populating this table. Often we know the pressures everywhere. Okay? So you also can make a quick diagram of this on a temperature entropy. That helps us. When you have 2 turbine stages, you'll have 3 distinct pressures, a high, an intermediate, and a low, right? Now, they're very close over here, but they're more distinct in the superheated region. But in the subcooled, they're pretty close together. And so what you do is you come out, you expand, you reheat, you expand, and then you condense, you pressurize, and there you go. So it's 1, 2, 3, 4, 5, and 6. Now, 4 probably and 2 could be slightly superheated, or it could be 2-phase in the dome. As I've showed them here, they're slightly superheated. 2 and 4 are slightly superheated. Okay, and so you just walk around the pressures. Now another problem I'm going to solve, and I solved last time, we started with 10 megapascal and 10 kilopascal. We'll just pick 1 megapascal for the intermediate pressure. But that could vary, just like 10 megapascal could vary. But it helps us put numbers and see how it works. So you put 10,000. Then at state 2, what's the pressure? 1,000. At state 3, what's the pressure at state 3? 1,000. Yeah, 1,000. There's no pressure drop. The pressure drops and the pressure gains are isolated to the pumps and the turbines. Through the condenser and through the steam generator, there's no pressure change. That's our first approximation. Real systems have friction in flow-in pipes. And then we have it drop down to 10, 10, and then back up. At state 6, what is the pressure? 10,000, right. And now you look at your temperatures. Maybe this is specified to be 440 degrees C, or 600 degrees C, or 580 degrees C, some degree of superheating. And now I know the temperature and the pressure. I like to think, okay, what 2 properties fix the state? Here for state 1, temperature and pressure. With that, I can get H and I can get S. Okay. Once I know H1 and S1, how do I work on state 2? Well, it's reversible expansion through that turbine, unless they give me some information about the isentropic efficiency of the turbine. Then I have 2 states, 2S and 2 actual. But that's just an extra layer of complexity. Right now we're just exploring superheating and reheating. So this S is equal to that S. S2 is equal to S1. Second law analysis around that first turbine stage. So pressure and entropy fixed state 2, then I could look up things like the temperature and the enthalpy at state 2. We go back to reheat. Often it's reheated back to some some temperature like 440. That's not specified like the temperature here. It's limited to be that temperature. So what we have is temperature and pressure, fix the state. We can get the enthalpy and entropy for state 3. How about state 4? Same as expansion through the first turbine stage, you do that just like that through the second turbine stage. And so the pressure and the entropy are used to calculate the temperature and the enthalpy at state 4. How about state 5? Saturated liquids. So the quality is what? 1? Or no, not 1. 0. It's saturated liquid. So it's the pressure, and you can put sat liquid or just put X for quality, and you know X is 0. And that allows us to get T, H, and S if need be. And then state 6. The pump always is a little curious. What you typically do is you just say, I'll calculate the work of the pump as VDP, and then I'll add that to H5 to get H6. So H6 is equal to H5 plus VDP. That's the work of the pump, VDP. So that's how a lot of times, or conceptually it's pressure and entropy. So pressure and entropy, or pressure and enthalpy. So there you go. Now, these problems take some time to work through, but there it is in a nutshell. Yes, sir?
So you said the reheat, they will tell us what it reheats to?
Often, yeah. Yeah.
It doesn't tell us, we assume it reheats to the initial temperature?
I can't think of any problem last semester, last year, and the last couple of years where that was a variable where you had to choose it. Now, in this, we have a design, and in here, you can play around with some temperatures to try to see how that affects efficiency in your design project. There, you may have to play with that temperature. But in a homework problem, it's typically specified. All right, so let's go through this. Here's a problem, and it's just the same problem that we outlined. 10 megapascal for the first pass in the steam generator. Comes out at 440 degrees C. It goes to 1 megapascal after the first turbine stage, and then it's reheated to 440, and then it's out of the condenser. The condenser is at 10 kPa, and saturated liquid comes out of the condenser. All of these are the types of things we just outlined. Well, I think we can make those calculations, and what I did here was summarize the solution to that problem and put it into to remind us where the states are, 1, 2, 3, 4, 5, 6, and also put it into a little matrix where I added the dead state, but here are the properties for state 1. Take a look at the pressures. Do they look right? 10,000, 1,000, 1,000, 10, 10. Yeah, look good. And then things like the temperature, 440, 440. And notice that for this problem, the quality at state 2 is 95%. So that state 2 came into the dome on our temperature entropy diagram. If we sketched it and tried to be accurate, you'd put a dome like this. You put the high pressure line like this, and an intermediate pressure line, and I'm not doing that so good. I need to flatten that dome out some more, like that. Okay. Put that like this, then like this, then like this. And so if we come out here, we expand, we get 95% quality at state 2. See that? Then we reheat up to that. So 1 to 3, the same temperature, 440. This is a temperature entropy diagram. And when you expand down to 4, the quality at state 4 is 92 or 3%. So it's in the two-phase region for those two states. Okay. So then we cross the condense at 5. I had drew these lines really bad there, didn't I? They need to be much, 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 much closer down here. Because when you put it through the pump, oh, it's straight up. And I didn't make it look very straight up on a TS diagram. But notice that the temperature is essentially the same. It may be 1 or 2 degrees. If you're using a computer program to evaluate the properties, you'll see the temperature's a little higher. Otherwise, it's not of interest to most of us. It's so close that it's 1 degree higher, it's the same temperature. So I just put the same temperature there for state 6. I didn't calculate, I just put the temperature there. All right. And notice that I got the specific volume in meters cubed per kilogram at state 5, such that I could calculate the work of the pump to be V5, that specific volume, times the pressure at 6 minus the pressure at 5. So that's how you calculated the work of the pump. Here are the numeric values in kilojoules per kilogram for the work out of the first turbine stage, that reheat, the condenser, the first pass in the boiler or the steam generator, work of the pump, second turbine stage. Q net and W net are both calculated and they check. And then what we find is that backwork ratio is really small, which is good, 0.7%. And the thermal efficiency is almost 40%, which is good. Okay. So if we come over here and compare what were the numbers that we had last time we talked compared to this. So here is a comparison of the ideal Rankine with superheat out to 440 in just one turbine stage versus having 440 in the superheat, then you expand it to 1 megapascal, then reheat to 440, so you have 2 turbine stages, the one we just calculated. And you see that there's a small improvement in the overall thermal efficiency. So probably 2, maybe 3 turbine stages are good. If you start to get 4 or 5, it probably appeals to your logic that it's going to be more complex to build, maintain, expensive, probably not worth the return in performance. So often in power plants you'll find good 3 stages, maybe 4, not 1. You'd have more stages, and you'd go back. You'd have all this piping going back for reheat, then coming out. All right. Well, that's one way to improve. You had reheat and you had superheat. Okay. What's the other way? Well, it's where we call it's regenerative Rankine cycle. It's where we have a feed water heater, a heater that heats up the feed into the boiler. Before it gets into the boiler, we try to bring that temperature up. And so they call it a feed water heater. The feed is into the steam generator or boiler. And you can have both a closed or an open feed water heater. Okay. So what I'm going to do is propose or sketch out how this would happen. And we'd also have superheat and reheat. So we'll keep those added features of superheat and reheat, but we'll add now an open feed water heater. So we'll put our steam generator here. We have our first pass through that steam generator. Then it comes out and goes into our first turbine stage. After the first turbine stage, it's starting to go back for that reheat. And it will go back for that reheat right there. Okay. But what it's going to do is it's going to divert some of the mass, not all of the mass, but some of the mass down to a feed water heater. It'll come down to this open feed water heater. Now let me finish out the diagram. This is a jump over, goes over to the second turbine stage. Out of the second turbine stage goes to the condenser. Out of the condenser, it goes into a pump. The pump goes into that open feed water heater. Now, this feed water heater is not all that special. It's just where two streams mix and have one stream go out. And so it comes out and it goes into, well, actually, yeah, it goes into a pump. And that pump then is what goes like that. Okay? So we have one turbine, two turbine, first pump, second pump, and we divert some mass after the first turbine stage. Instead of reheating it, we bring it down to an open feed water heater. And what it does is this temperature right here going into the steam generator is higher than it would have been without that open feed water heater. Okay. You want to make a table of properties or list the properties. Let's go ahead around and just mark them. State 1, State 2, State 3, State 4, State 5, 6, 7, and 8. So we have 8 states, okay? Well, let's put on a temperature entropy diagram. Okay, let's put our line of constant pressure high, another line of constant pressure intermediate, and a line of constant pressure low. And we have somehow, because of temperature limits, we've taken that to the limit there, okay? So we're going to bring it down and then do that, and then bring it down and then condense. And now, if we just condensed and put it up to this high temperature right here, or this high pressure, all of this heating would be used to heat up the cold feed water. And our goal is to get the feed water hotter without burning coal to do it, our expensive fuel source. So we look around in the power plant, we say, hey, there's some steam over there, it's very hot. Let's take a little of that steam to mix it with the, and now that heating is internal to the cycle and not used. This temperature, this from 6 to 7, it's much higher temperature at 8 and 7 than you could achieve without this open feed water heater. All right, so let me try this. And we'll have numbers for this in a minute, but you understand it by visualization. So this is always tricky to do because it misrepresents the facts. These would have to be very tight and very, very tight. And so the pressure, the temperature's right there. That would normally be the temperature that goes into the feed water heater, but that's the temperature at state 6. And we mix it with some fluid having the enthalpy and the temperature at 2, such that it comes out at 7, and 7 wants to be saturated liquid. We want 7 to be saturated liquid at that intermediate pressure. So from 6 to 7 is heating within the system, not heating done by coal or natural gas or whatever my fuel source is. Then we put it through another pump to put it at 8. And then 8 up is now heat from burning my coal or natural gas. And go across and up. Okay? And I say natural gas. Most people don't use natural gas to boil water. Next chapter we study gas power cycles. You'd use a Brayton cycle. But they used to have natural gas. They would burn it to boil water, but you don't do that now. 3, 4, 5, 6, 7, 8. There's all your states on this TS diagram. And when you analyze a problem like this, you want to go ahead and make a property table. So pressure at different states and temperatures at different states, 1, 2. I'm not going to be able to flush this all the way out because I have it on another slide with all the numbers. But look at the pressures. If you can get the pressures correct at every state, usually you can do pretty good. So the pressure at 1 is the high. What about the pressure at 2? High, intermediate, or low? Intermediate. Pressure at 3? Intermediate. Pressure at 4? Low. Pressure at 5? Low. I have 2 pumps. That's a clue. Pressure at 6? Intermediate. And it has to be the same pressure as the pressure at 2, doesn't it? Because they're just mixing. They're just mixing. At 2 and 6 have the same pressure. So the pressure at 2 is equal to the pressure at 6. How about the pressure at 7? It's just coming out. So guess what? The pressure at 2, the pressure at 6, the pressure at 7 are all the same. Then we go, that's an intermediate pressure. Then we go to pressure at 8, that's back to high. True? So if you march around and get your pressures right, it'll really help you. And then go ahead and get your enthalpies. If you know how to fix the states, it's just adding just a little more complexity, but we want saturated liquid coming out of the condenser, and we want saturated liquid coming out of the open feed water heater. The way that you determine how much you bleed off, and they put a parameter y here. Y is the mass fraction that comes out of the first turbine stage that's diverted to make the open feed water heater work. Y is something like 40% or 30%. Okay, it's just a fraction. But what is it? It's going to be the mass that's diverted to feed the top of the open feed water heater, that's this mass flow rate right here, divided by the mass flow rate going out the first turbine stage, or what went through the first turbine stage. So if that is the fraction, what is the fraction that continues on? 1 minus y, true? Does that make sense? Right. So let's do this. Do a mass balance. And just write it like this. Do a mass balance for this open feed water heater right here. Okay? If you do that, what you find is that the amount that went back for the reheat, this is how much went back for the reheat. It goes through the second turbine stage, goes through the condenser, goes through the first pump. That's what feeds into the open feed water heater. So the mass flow rate that went for the reheat plus the mass flow rate that came to the top of the open feed water heater is equal to the mass flow rate that goes into the second pump, which is the same as the mass flow rate that goes into the first turbine stage. Because what goes through the second pump goes through the steam generator on that first pass, goes into the first turbine stage. So just write this like T1. Take this equation, divide by m dot T1, m dot T1, m dot T1. Recognize that this is our definition of y. And so we have, and this is 1, so we have y is equal to 1. This is that mass flow rate fraction that goes for the reheating, and you just conclude that this is 1 minus y. I don't know if that's too obvious, that if y is diverted down, 1 minus y continues. True? So sometimes I'll write, well, this is 1 minus y continuing, 1 minus y continuing, 1 minus y continuing, 1 minus y continuing, and they join up. Now I'm at 100%, 100%, 100%, and then we split. We split right there after the first turbine stage. Once we have the mass flows correct, then we go and do an energy balance. If we do the energy balance for the same open feed water heater, it tells us what y has to be. It gets our equation so that we know, oh, if we want saturated liquid at state 7, y has to be 31.2%, whatever number it has to be. True? So that's what we're going to do. If you do an energy balance, you'll have that the mass flow rate coming down to feed the top of the open feed water heater multiplied by its enthalpy, which is enthalpy 2. Isn't that the enthalpy coming down? H2. You add that to the mass flow rate coming from the first pump, Well, the first pump is what went on through, well, just put P1 there. The mass flow rate coming through the first pump, multiply that by H6, and that has to equal the mass flow rate going to the second pump times H7. True? Is that true? So if you divide the whole thing by, let's say, the mass flow rate, the second pump, you'll get H7 is equal to pump 1 divided by pump 2. Isn't that 1 minus Y times H6? And then this is M dot pump 2 and then M dot pump 2. And then mass flow rate that comes down the open feed water heater divided by the mass flow rate through the second pump, which is the same as through the first steam generator. This ratio is, what is that ratio? Y. And so now we have this one equation with one unknown, and you find that Y is equal to H7 minus H6 divided by H2 minus H6, if I did that right. Double check me on that. Did I do that right? Does that look reasonable? How many people, give me a thumbs up, agree? 2, 3, 4, 5. Does it look good? Any others? All right. Well, once I know that I want saturated liquid here, and I know the pressure at state 2, and we know the enthalpy because we expanded isentropically from 1 down, then we can calculate a lot of other parameters. Let me show you some data. Well, first of all, that was just put up there almost for that same reaction I just got. These problems are long, but you just go slowly working through the cycle as I tried to show you for the mass flow rates and the pressures. And then, okay, which two states help me fix this the rest of the properties? And what you can do is you get a table of properties like this one. This is for the same. Here I've resketched it. So I have state 1, 2, 3, 4, 5, 6, 7, 8. Do we have the same state 8 states that we had before? We have the 2 turbine stages, the 2 pumps. We have the 2 Qs that are in the steam generator, the first pass and then the reheat pass. And then we have the Q out of the condenser. In order to calculate all those, I just need to get a table of properties, state 1 through state 8, temperatures and pressures, and here are the enthalpies, which are the keys. But you build this slowly, okay? And once I have built up the enthalpies, then it's easy to calculate the work of the first turbine stage. What is the mass fraction that's diverted to feed the open feed water heater? For this problem, 23%, 22.87%, leaving 77% to continue on through the system. Okay? Now, what we're going to do is we're going to try to get an overall thermal efficiency for this cycle. It's calculated to be a whopping 52%. That's tremendous. It's really good performance. Okay? But what we have to do is work up slowly to that thermal efficiency. Notice the back work ratio is low, like we've seen before in other systems, because the pumps are just boosting the pressure, and they're very efficient at doing that. But this thermal efficiency, if we work backwards, what is the equation for the thermal efficiency? Is it the work net out, which would be the work of the turbine 1 out plus the work of the second turbine 1 out, second turbine out, minus the work of the first pump in, minus the work of the second pump in? Would that be what we really want, net power out, net work out? Okay. And then we have divided by the Q in, that would be Q of the steam generator plus Q of the reheat. True? Okay. A lot of times we calculate the Q of the steam generator. If you remember, what was the equation for that Q of the steam generator? Was it the mass, was it the enthalpy at 1 minus the enthalpy at 8? And it has units of kilojoules per kilogram. We have to really pause and think. That per kilogram is how many per kilogram going through that section, right? When we calculate Q of the reheat, it's going to be H3 minus H2, right? And it's so many kilojoules per kilogram. If I have 1 kilogram flowing through or into the first turbine stage, how many kilograms do I have? 1 kilogram flowing into the reheat section, or do I have less? Do I have 1 kilogram or less? You have less. And so what we do is put everything on the same per kilogram scale. And the same per kilogram scale is the kilogram that goes into the first turbine stage. That's the notation in the textbook. So I'll try to stay with that notation. So this kilogram is what went to reheat. But if I multiply by kilogram reheat divided by kilogram first turbine stage, those kilograms cancel, and I've modified it. So what you end up doing is I've tried to write it right here 2 ways. This is the Q that's going in the reheat, but it's either per kilogram that goes through the reheat, or it's per kilogram that went through the first, through the steam generator and into the first turbine stage. Notice it's smaller. What you did was you multiplied by 1 minus 1. This ratio right here is 1 minus 1. 1 minus y. Did I say 1 minus 1? It's 1 minus y. And the same goes for over here for the condenser. You want the heat released out of the condenser per kilogram that goes into the first turbine stage, not per kilogram that goes through the condenser. You just multiply by 1 minus y. All right? Let's see. That's why we have a couple different notations here. But whenever you put them all on the same per unit mass basis, check your work, make sure that these are okay, and then you have greater confidence in your calculations. So let me do this one right here. See this one? This is the work out of the second turbine stage per kilogram that goes through that second turbine stage. But if you want it per kilogram that goes through the first turbine stage, it's smaller. It's 1329.21 minus times 1 minus y, or 0.7713. Such that all of these terms here have the same units. Okay? Thank you for your attention. We'll see you.